Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about a CMOS NAND gate and XOR gate. And these gates are fundamental gates to any type of digital electronics. So in this lecture, I will be introducing them. And in order to understand the NAND and the XOR gate, we need to first understand the CMOS inverter, which I talked about in my previous lecture, which is labeled CMOS inverter voltage transfer characteristics. And I will put a link in the video on the top right-hand side right now. So in order to understand the CMOS inverter, a quick review, we need to realize that this is an NMOS here. Let me use a different color. This is an NMOS, and this is a PMOS. And in an NMOS, from our previous video, we realized that when VGS, which is equals to VG minus VS, is greater than VTN, the NMOS is on. And for reference, VGS could be, let me use a different color here. VS for NMOS is always 0 because it's ground. VGS, when it's 5, is always greater than VTH, which is equals to 0.7. Or I could write it like 0.7. This is equals to 0.7. So it's on. And when VGS is equals to or less than VTH, we consider this off. Or we could say that when VG minus VS is equals to 0 minus 0, which is less than 0.7. In this case, VG is 0 and VS is 0. The MOSFET is off. And then for PMOS circuit, from our previous lecture, we said that when VGS P, so in this situation, this was N, and this was N, VT and N, and this is N. When VGSP is less than VTHP, then the PMOS is on. And in this situation, for a PMOS, this is VG minus VS, and for a PMOS, for it to be on, VG has to equal 0 minus 0, or sorry, VS is 5 in this case, because in the PMOS, this is VDD, and this is terminal S, this is terminal D, this is terminal D, and this is terminal S. So VG minus VS, which is 5, is equals to negative 5, which is less than negative 0.7. So VTH is negative 0.7, VTHP. So this is on. And for VGSP greater than VTHP, we consider that this is off. Or we could say that VG minus VS is equals to 5 minus 5, which is equals to 0, which is greater than negative 0.7. So this is off. Now, what does this tell us? This tells us that when I have an input, so this is G right here. When I have an input G, when G is equals to 0, for the NMOS, we get a situation that looks like this. So NMOS is off, but PMOS is on. As a result, V out if we can imagine that this here is V out and this is V in, V out will be equals to a VDD, which is 5 volts. All right, it's this situation here. So it's on, so it's pulling that VDD, which equals to 1. G is equals to 0 means that Vn is equals to 0. And when G is equals to 5 volts, which means Vn is equals to 5 volts, the NMOS is on, but the PMOS is off. And V out is equals to, in this case, this is the case here, so V out is equals to 0 or ground, which is equals to 0. So in summary, we can say that the NMOS and the PMOS complement each other. That's where we get the complementary term in the name CMOS. Again, MOS stands for metal oxide semiconductor. And we could say that we can have a switching function. So basically, if Vn has a function like this, where we say it goes from 0 to 1, then V out will have a function like this, where it would go from 1 to 0. Again, this is explained in more detail in the previous video called CMOS inverter VTC, clearly explained. But we can then simplify it and say that if you have an NMOS and it looks like this, this is a voltage VG, this is your output, or you could say that this is ground when this is 1, it's connected to ground, and when it's 0, it's not activated, so we don't get an output. Or another way to think about this is an NMOS, when my input is high at 1, is a closed circuit. So this is 0, this is 1, is a closed circuit that pulls a 0, because this is a ground, to its output. This is ground. And when it has an input of 0, it's an open circuit. So this is how we can think about an NMOS when it comes to VGS switching in a step function. Next, we want to think about the PMOS. So for a PMOS, we consider this is grounded, this is a voltage VDD, which is connected to terminal S, and the output is taken from here. We put a circle here, and this is a voltage VG. And we say that when you have a high VG, or a VG of 5 volts, this is VDD, we pull, this is 1, we pull nothing because this is an open circuit in a PMOS. And again, this looks something like this. So this is just an open circuit. And so it's an open circuit for a PMOS. And for when the VG is 0, so this is VDD, it pulls a voltage output VDD. So this is 0. And what it looks like is a closed circuit. So this is a closed circuit. And again, just to be, as you can see here, they complement each other. So when there's a 1, the NMOS acts as a closed circuit, but the PMOS acts like an open circuit. And when there's a 0, the NMOS acts like an open circuit, and the PMOS acts like a closed circuit. So we can say that the NMOS and PMOS complement each other because they are opposite. Next thing we're going to do is we're going to talk about the NAND gate. So this is we're going to draw it out in real time, and we're going to talk about it. So this is the NAND gate. And the NAND gate is made up of 2 parallel PMOSes, something like this. This is out. And 2 in series NMOSes. So this is N2, N1, P1, and P2. This is VDD, VDD, and these are connected like this. This is A, this is B, and A connect and B connects. Remember, this loops over to here. So that is your NAND gate configuration. And if you remember the truth table of a NAND gate, A, B out is 0, 0, 1, 0, 1, 1, 1, 0, 1, and 1, 1, 0. And so we're gonna try and, based on what we've learned up here, we're going to try and prove that this goes to this. Okay? So the first thing we're going to do is we're going to put 0 and 0 in A and B. And I'm going to switch colors here, and I'm going to write it out in terms of the zeros, the 0 functions like such. So we're going to write it like this, and what we can do is basically say whether or not these circles are in a closed loop or an open loop. A closed circuit or an open circuit. So if we say that A is equals to 0 and B is equals to 0, this is a PMOS. Sorry, this is an NMOS. So this is open at 0. These NMOSes are open at 0. And the PMOSes are closed at 0. So my circuit is going to pull. So here we get a track. So this goes like this. And this 0 goes here. So it pulls VDD, or V out is equals to 1, which is what we get right here. So that's correct. And then I'm going to erase this. So for my next term, I'm going to consider this term right here, where A is 0 and B is 1. And as you can see here, the NMOS here is closed because it's a 1. B is 1. The NMOS here is open because A is 0. The PMOS here is closed because A is 0. And the PMOS here is open because B is 1. And what's going to happen here is this is the only path to ground. As a result, my V out is equals to VDD, which is equals to 1. And as we can see, it's depicted here. Let me go ahead and erase this now. And next, if B is 0 and A is 1, so this is equals to 1 and this is equals to 0, my NMOS down here is going to be open circuit because B is 0. My NMOS down here is going to be closed circuit because A is 1. My PMOS up here is going to be open circuit because A is 1. And my PMOS here is going to be closed circuit because B is 0. And as a result, the only path that flows is right here. So V out is equals to VDD, which is equals to 1, as shown here. And then the last case is when both A and B are equals to 1. Both A and B are equals to 1. And we could depict that 1, 1. And what happens here is both NMOSs are closed circuit and both PMOSs are open circuit. And so the only path that it will flow will be from here to my V out, or from here to my V out. So V out is equals to 0, or ground, which is equals to 0. And we get this. And that is your NAND gate. And a quick tip, the NAND gate is symbol like this, where this is A and this is B. And if you put a NAND gate and a inverter after it, A, B, C, you get what's called an AND gate. And if you remember the truth table of an AND gate, AB out, 0, 0, 0, 1, 1, 0, 1, 1. Basically, this is 1, 0, 0, 0, which is the opposite of this. And what we'll notice is that the AND gate is considerably more harder, or in terms of hardware, we need more. We need to include another PMOS here. We basically have to include an inverter here. So that takes more hardware, so it's more space. So we would rather use a NAND gate in our digital design. The next thing I'm going to be talking about is the NOR gate. And what I'll do is I'll draw it out, and then maybe you can pause the video and see if you can use the same concepts we used here to find the truth table for the NOR gate. So this is the truth table for the NOR gate. And as you can see, we have now the PMOS is in series and the NMOS are in parallel. And the truth table for this, the truth table is A, B, and the out is 0, 0, 0, 1, 1, 0, 1, 1, and it's 1, 0, 0, 0. It's the opposite of the OR gate, or the opposite of the OR gate, or it can be called the NOR gate, or not OR, right? It's an OR gate, but then there's an inverter after it. That's where the not is coming from. And here I have the same block diagram as we did up here, right? And we're going to analyze it to make sure that our truth table is the same, is correct. So imagine you have A is equals to 0 and B is equals to 0, as we see in this situation. So that would mean that our PMOSs are on, so these are closed circuits, but then our NMOSs are open circuit. So the switch of the voltages are going to pull V out is equals to VDD, or 1, which is located right here. In the next case, erase this. We have that A is equals to 0 and B is equals to 1. So that means since A is 0, this PMOS is going to be closed. This NMOS is going to be open because B is equals to 1. And we have a situation where A is equals to 1, or A is equals to 0, and B is equals to 1. So this PMOS here will be closed. This PMOS here will be open since B is equals to 1. But this NMOS down here will be equals to close because B is equals to 1. And this NMOS here is going to be equals to open because A is equals to 0. And so our current, or this switch, is going to be open, pulling V out equals to 0, as we see the corresponding things right there. And then if we consider when A is equals to 1 and B is equals to 0, this PMOS here will be open because A is equals to 1. This PMOS will be closed because B is equals to 0. This NMOS here will be equals to open because B is equals to 0. And this NMOS here will be closed because A is equals to 1. So this switch is open, pulling V out to 0 as shown here. And last but not least, when A is equals to 1 and B is equals to 1, my PMOSs are open circuit and my NMOSs are closed circuit. As a result, this switch pulls and this switch pulls, V out equals to 0 as shown here. Now the symbol for an OR gate or a NOR gate looks like this. A, B, and there's a open circuit, there's a circle right there, where this is the NOR gate, but for an OR gate, it looks something like this. But in order to create an OR gate, so this is an OR gate, A, B, we need to include a inverter in front of our NOR gate, making it to have more hardware. So this is equals to this, making it having more hardware. So again, in digital electronics, we use more NOR gates than OR gates simply because it requires less hardware. And this is the fundamentals of digital electronics, and we can go ahead and create things like a full adder. And I will talk about that in my next lecture video. And with that being said, if you like the video, please give it a thumbs up. Please subscribe to my YouTube channel, share my videos, and I will see you in the next one. Thank you.